In this video, we're going to talk about how to apply Extrema or finding Extrema to word problems of a variety of different types. So this is applications of Extrema, or it's often called optimization. Okay, so that's how you might see it other places. So let's just jump into an example. So this is one that you might be able to find the solution for without calculus, but I'm going to show you how we use what we've learned in this class to find the solution. So suppose that we know the product of two positive integers is 225. Okay, so when you multiply them together, you get 225. We want to find the two numbers so that their sum is a minimum. Okay, so we want the two numbers that have the smallest sum with a product of 225. So the hardest part about these type of problems is to make the equations that you need. Okay, so what we're going to do, so that's why I tried to start off with something kind of basic. So I don't know what my numbers are. So what I want to do is give them letter names. Okay, so let's let x and y be the two numbers. Okay, so we know that they're positive integers, so we know x and y are bigger than 0 and integers. Okay, so we should get an integer. Now we also know, so the product equals 225. We can write this as an equation by saying x times y should equal 225. Okay, so this is one equation that we have to work with. So we know that that should be true. This sometimes we call the constraint equation. Okay, so it's not the thing that we want to minimize, but it's another equation that we have on our variables that needs to be satisfied. So what we actually want to do is we want to minimize the sum. Okay, so I'm going to call that S. Okay, so this S represents the sum. Okay, and S is going to be x plus y, right? Because that's how you do a sum. Now, what I want to notice here, so, okay, how would we normally find the maximum or minimum? We want to find the critical numbers and see if they're relative maxes or mins, or if they're on an interval, some type of method like this. But here we have s, x, and y. So I notice that I have too many variables. Okay, so even if we were doing implicit differentiation, there's only ever x and y. So here I think there's too many variables going on. So what I want to do is I want to try and get rid of one of them. Okay, so what we're going to do is use the constraint to eliminate one variable. Okay, so x times y equals 225. If I solve for y, that means that y is 225 divided by x. So then I can plug that into the sum and say that the sum should be x plus 225 over x. Or maybe I want to write that as x plus 225 times x to the minus 1. Okay, this is my sum. And this is the thing that I want to minimize. Okay, now maybe I'll just make a note here. Sometimes we call this the objective function. So our objective here is to minimize. So if I want to find the minimum, I need to know the domain and I need the critical numbers. Okay, so we know the domain for x, so it has to be bigger than 0. So it goes from 0 to, and then y is an integer. So the biggest x could be is 225. Okay, and it's an integer, but we'll just leave it like that. Oh, maybe I'll write and is an integer. So it's hard to write that they're integers. So we know we have an open interval. I guess it could equal 225, but it can't equal 0. Okay, so now I only want critical numbers that are in that domain, so I can throw out negative ones if I happen to get that. Okay, so we want to find our critical numbers. So that means that I want to take the derivative, I want to take the derivative of the sum, because that's the thing I want to minimize. So I take the derivative. Now I'm going to take the derivative from here. Okay, so s is equal to this equation. This happens to be the easiest to take the derivative of. So it's going to be 1 minus 225 x to the minus 2. Okay, so written another way, that means s prime is going to be, so this is 1 minus 225 over x squared. So if I make a common denominator, it's going to be x squared minus 225 over x squared. Okay, so this is my derivative equation. Okay, so we're going to be using that. Okay, so I want to find the critical numbers. I want to take the derivative, set it equal to 0. Okay, so that means that 0 is equal to x squared minus 225 over x squared, which means that the top is equal to 0, which means that x squared is equal to 225, which means that x is plus or minus the square root of that, which happens to be 15. Okay, so x is plus 15 or minus 15. Now, we can get rid of, actually maybe I'll just write these separately. So this means that x equals negative 15 or x equals positive 15. And now we can get rid of this one since it's not in the domain. Right? X was a positive integer, so it cannot be negative 15. So I get one critical number there. Okay, now I also need to think, okay, where does the derivative not exist? Okay, so that's going to be when the bottom is 0, so when x squared is 0, so that's when x is 0. Again, though, this one is not in the domain. If x is 0, there's no way I could multiply it by a y and get 225. Okay, so I know the constraint is not satisfied. It's not a positive number, so we can throw it away. So our only critical number is the x equals 15. Only one in our domain, I should say. So that's likely going to be the where the minimum occurs, but we want to check that it is a minimum. Okay, so there's lots of ways you can do this. You could take the second derivative, you could use the second derivative test. I'm just going to use the number line. So the smallest maybe is 0, and I guess it stops at 225. Okay, 15, let's put it here. So I want to check a number on each side. Let's say I check 1, or it doesn't matter, it could be 2. Okay, any number here. And I plug it into the derivative, so s prime of 2 is going to be 4 minus 225 over 4. Okay, this is definitely going to be a negative number, which means I'm decreasing. And then if I plug in, let's say 20, I'm going to have 400 minus 225 over 400 for my derivative. This is definitely a positive number, so that means I'm increasing, which means that it looks like here I'm going to have a relative minimum. Okay, because it decreases and then increases after. Because it's the only critical number, so by the critical point theorem that we talked about in the last video, S is continuous on our domain, so on the interval, and at x equals 15, we have a relative minimum. So that means that x equals 15 has an absolute minimum there, which is actually what we're looking for. Okay, so now we know that that's where our absolute minimum is. We can find the other number. Okay, so if x equals 15, that means that y is 225 over 15, which happens to also be 15. So then our smallest sum is s equals 15 plus 15, so 30. Okay, so 15 times 15 is 225, and the sum is 30. Now you could actually check. Okay, so others that would work but have a bigger sum, I think I have 25 and 9. I think that those multiply to 225, but then s is going to be 34. Okay, so that's bigger. You could have 45 and 5. Okay, but that's going to give s equals 40, etc. So there's any way that you can have it where they multiply to give 225. Their sum is going to be bigger than the sum of 30. This is the smallest possible sum that you could have. Okay, so this is an example of an optimization problem. So notice the thing that you want to be aware of is that we're trying to find the maximum or the minimum of some quantity. Okay, this is how you can distinguish this type of word problem from some others that we're going to encounter. So what did we just do here? Okay, so what is the method that we used? So read the problem carefully. I always put that for every word problem. Take the time to actually read it. What you need to be aware of is you want to know what is given and what is unknown. Okay, so you want to know, and especially in these types, what is to be maximized or minimized. Okay, so that, and for this type, that's very important. Okay, now, if possible, so some of these examples, a sketch will be useful. Okay, this can help you, can help define variables. Okay, so if you can label them on the picture, if you have a picture. Okay, so the last example did not didn't have a sketch that was associated with it, but a lot of them do. So there's going to be one variable that is to be maximized or minimized. So like I said, this thing we call the objective function. Okay, so you want to know what this is. So you're going to want to express this in terms of your other variables. Okay, now in particular, you will need to reduce, if there's more than one variable, you're going to need to reduce to only one variable. Okay, now here is where you use the constraint if there is one. Okay, so sometimes your objective function will immediately be in terms of one variable. It kind of depends how you define your variables. But if it's in two variables, it means that there should be some constraint function that you can use to reduce to only one variable. Okay, so we're not doing multivariable calculus, so we only can take the derivative when there's sort of one variable only. And you shouldn't need to do the derivatives here implicitly. So the domain you need to determine the domain of your function, and it needs to make sense in the context of the problem. Okay, so sometimes it won't be obvious. It won't tell you the domain. Like this one, the last example told us that the numbers were positive integers, so we kind of knew that. But for some it doesn't. Okay, but if you're making a fence and your variable is a length, okay, you should know that the length cannot be negative. Okay, so that's what I mean by make sense in terms of the context. Okay, so then from your function in step 3, so from your objective function, you want to find the critical points or the critical numbers. So here's where the calculus comes in. So we take the derivative, okay, set it equal to 0 and dne. Okay, and then you're going to keep critical numbers that are in the domain. Okay, so you're allowed to get rid of the ones that don't make any sense. Okay, and then you need to check that your critical number is a maximum or a minimum. Okay, so there's a famous problem where someone didn't do this step and they just assumed it was the one that they wanted, and it turned out not to be. Okay, and bad stuff happened. So you want to make sure that you in fact got the minimum, and there could be more than one, and then you definitely have to check. But if you only get one, don't assume it's the right one. So there's different ways you can check. So if your domain is a closed interval and your function is continuous on that domain, then you can use the EVT, the extreme value theorem, and then you just have to evaluate each critical number and each endpoint. Oops. To see which one has the biggest or smallest value. So the extreme value theorem will tell you that the absolute max or min definitely exists, and you know it has to be at the critical number or at the endpoint. So you just need to see which one. So you can just check their y values or s values or whatever the values you get when you plug it into your objective function. Okay, now if you have a domain that's open, so an open interval, so you basically, if you can't use the first method, you can't use the extreme value theorem, but you have only one critical number, then you can do what we used in the previous one, and you can use the critical point theorem. Maybe I should just write it all down. Okay, so you can use the critical point theorem. So when you do that, you just need to check whether the critical number is a relative max or min. Okay, so you can do this by, via the increasing decreasing method. So the first derivative, actually I should just write first derivative test. Okay, or the second derivative test. Okay, so that's how you can classify. If it's the right one, if it's the right relative one, then it has to be the right absolute one. Now, if you have an open interval, so you can't use, maybe I should just write this. So open interval, what I mean by this is essentially you cannot use EVT. Okay, so in this last case, you have an open interval, so you're not using EVT, the extreme value theorem, and you have more than one critical number. That means you cannot use the critical point theorem. Then what you have to do is basically try to use the critical point theorem. So you want to classify each critical number as relative max or min. or neither. Okay, so you want to see if they're relative maxes or mins, but you also need to consider the limits at the endpoints. Okay, so whether they're infinity or not, like they're open endpoints potentially. So you want to see if there might not be. Okay, so here you might not have a max or min. Okay, so you want to be careful. You need to think about the endpoints at least. So that's sort of the method. So let's try another example. So Kaylin and Adam are making a chicken coop to house 2 sets of chickens, old ones and young ones. Okay, and apparently you have to keep these chickens separate when you get new ones as they fight each other. So what they want to do is enclose 2 equal sized rectangular fields, okay, that share one side of fencing. And they want the pens to have a combined area of 12,000 meters squared. So they're making giant pens. They know the exterior fence costs $50 a meter, and the interior fence costs $20 a meter. What are the dimensions of the pen that minimize the cost? Okay, and what is the minimum cost? So there's a lot going on here. Okay, so let's just write down a few key things. So we know the total area is 12,000 meters squared. Okay, and we know the outer fence is $50 per meter, where the inner fence is a bit cheaper. So it's $20 per meter. And we kind of know what our pen looks like. Okay, so it's going to be something like, so they share an inner fence. Did I draw those? Maybe I'm not quite in the middle here. So they should be equal sized pens. So this line should be right in the middle. I don't know, maybe that's a bit better. So I'm gonna, so this is pen 1 and pen 2. So I'm going to start by defining some variables. So I don't know the size of my pen, okay, and I'm going to need the size in order to do anything, essentially. So what I'm going to do is, let's call the sort of height of this pen y, and maybe the length x. Okay, now because these pens are the same size, I know that this length is also x. Okay, and obviously this length is equal to y. Okay, now you could define your variables in a different way. Maybe you make the whole bottom, so you might call this whole thing x, and then this part would just be half of x. Okay, that would be totally fine. Okay, there's different ways to label your variables. Okay, but those are the variables I'm going to use. Okay, and now the outer fence, let me just let's highlight. Okay, so the outer fence is all the fence that goes around the outside. Okay, but the inner fence is just this one bit in the middle. Okay, so that's where we need our fencing. So what I want to do is minimize cost. The cost. Okay, so I want an equation for the cost. So I'm going to call it C for cost. Okay, so how would I compute this equation? Well, the costs are different if I'm on the outside or the inside. So I need to buy all this fencing material. So I want to know how much meters of each I need. So if I think about the inner fence, it has length y, right? Because each of these sort of vertical lines has length y. So I need y meters of that fence, and I know it's $20 per meter. So the cost for the inner fence is going to be 20 times y. Okay, now to that, I want to add the cost of the outer fence. Okay, so it's $50 for each meter of outer fence. Now, how many meters do I need? I need X meters for this part, X meters for this part, X meters for that part, and X meters for that part. So I need 4X amount for these horizontal sides, and also 2 Y's for these vertical sides. So I'm going to have 50 times 4X plus 2Y. Okay, so this is number of meters of outer fence required. So then when I multiply it by 50, I get the cost of the outer fence. Okay, now if I simplify this, so I'm going to have 50 times 4 is 200x, and 50 times 2 is 100, plus the 20, I get 120y. Okay, so this is what I want to minimize. Okay, so we want to minimize this. This is our objective function. But notice too many variables. Okay, so because there's too many variables, we need a constraint. Okay, so what is constraining the size of our pen? Well, I have a total area that I want. Okay, so the area is an issue. Okay, so I know that the area should be 12,000. How do I compute the area? Well, the area for a rectangle is length times width. Now my length, the way I've defined my x's, is 2x times y. Okay, so I'm going to have area is 2x times y. So if I want to get rid of a variable, maybe the y, I solve, okay, wait, actually, so right now I have area, but I know the area, oops. I know the area is 12,000, so I can plug that in for A. So 12,000 is 2xy, which actually, okay, that's fine. So then if I solve for y, I'm actually going to get 6,000 over x. So now we can reduce our cost equation. Okay, so rewriting the cost equation, we have C is equal to 200x plus 120 times 6,000 over x. Okay, so this I can simplify to 200x plus 720,000 times x to the minus 1. Okay, so this is our cost. This is the thing we want to minimize. And now we have only one variable. Okay, let's just take a moment to think about the domain for this. Okay, so we need x and y both to be positive since we can't have negative lengths. But because they could be like part of a meter, we can't really say, we don't really know the maximum. Okay, so what I'm going to use is just x in the interval from 0 to, so not including 0 to infinity. Okay, that is enough. I won't be able to use the extreme value theorem because it's not a closed interval. So I'll have to use one of the other two methods. Okay, but that's what I'm going to use for my domain. That makes sense to me. So we want to minimize this equation. Oops. So when we want to maximize or minimize, what we're going to do is take the derivative. Okay, so now that we have C in terms of only x, okay, we're able to take its derivative. Okay, so C prime, and maybe I just want to say, so the reason I want to take the derivative of C is because I want to minimize the cost. Okay, so I have the equation of the thing I want to minimize, so that's why I want to look for its critical numbers. Okay, so C prime is going to be 200 minus 72,000 x to the minus 2. Okay, which is 200 minus 72,000 divided by x squared, which we could write, if I make a common denominator, as 200x squared minus 72,000 all over x squared. Okay, so that's our derivative. So find critical numbers. Okay, so I want to set C prime equal to 0. So that's when the top is 0. Okay, so then if I solve, so you could either factor, so I could pull out 200, or I can just solve for x squared. So 200x squared is equal to 72,000. So if I divide both sides by 200, I get x squared is 3,600. And if I take the square root of both sides, x is plus or minus the square root of this, which means that x is minus 60 or x is plus 60. Okay, now again, minus 60 does not make sense. X is a length. Okay, so x equals minus 60 doesn't make sense, which means that it's not in the domain, which we already said was x bigger than 0. Okay, now when C prime doesn't exist, that's when the bottom is 0, so that's when x squared is 0, which means that's when x is 0. And again, this one you could keep, but I think it's not in the domain, because if one of my lengths is 0, it means that one side length is 0. It means I don't have a pen. Okay, so this is like no pen at all. If one side is length 0, I just have a strip of fence. Okay, and that's definitely not going to house Kaylin and Adam's chickens. So I think we should get rid of that. So our only critical number is x equals 60. So we want to check, we want to use the critical point theorem. I am going to use the second derivative test just to be different. Okay, so let's check. X equals 60 is a relative minimum. Okay, so here I'm going to use the second derivative test, which remember you do not have to use this test. Just because we did the other test last time, I want to do a different one. So I want to compute the second derivative. Okay, so let's go up and look at the first derivative. Now it's going to be easiest to take the derivative from the sort of not simplified version. Okay, so here I'd have to use the quotient rule. I don't want to do that. Here I don't. Okay, so derivative of 200 is 0. And then here I just bring the negative 2 down, and then it's going to be a negative 3. So it's going to be negative 72,000 times negative 2x to the negative 3. Okay, so that's actually 1,044,000 divided by x cubed. Okay, so then if I do C double prime evaluated at 60, I'm going to have this big number, this big positive number on top, divided by 60 cubed. Now I don't care what this number is, I know it's a positive over a positive. So I know it's a positive number. So that means that C is concave up there at x equals 60. Okay, so if it's concave up and c is our critical number, it actually has to be at the bottom. Okay, so that means that x equals 60 has a relative minimum. Okay, so then by the critical point theorem, x equals 60 has an absolute or global minimum. So now we know we have the right point. Okay, so this is where it is. Now I encourage you to go back up and read what the question wanted. Okay, so here it says, what are the dimensions of the pen with the minimum cost, and what is the minimum cost? Okay, so we want to find both the dimensions and the minimum cost. So I know x, I need to find my y value. Now it's easiest, I have used the constraint to solve for y, so it's going to be easiest if I use that again. Okay, so when x equals 60, y is 6,000 over 60, so y is going to be 100 meters. Okay, so the dimensions of each pen are 60 meters by 100 meters. Okay, and the minimum, well, maybe I should say actually, the dimensions of each pen that give a minimum cost is 60 meters by 100 meters, and the minimum cost is C equals, so then you can use either equation. Because I have x and y, I'm going to use this one here. If I didn't need the y value, then I would probably use this one so that I didn't have to find it. But it's totally up to you. Okay, so here I'm going to use the top one. So it's 200 times x plus 120 times y. So it's 200 times 60 plus 120 times 100. So if you compute that, the cost is going to be $24,000. Okay, so this would be our final answer for this question. So you should get in the habit of answering the question, making sure that you've answered what the question asked, and you should use a sentence for that. So that's an example of an optimization problem.